All right, so this is a bonus video. We did some examples with both geometric series and telescoping series, and we also talked about the nth term test for divergence. But I wanted to give you a couple of examples where we actually try to start applying these techniques and identifying what is the appropriate technique for a given problem. All right, so we're going to look at a couple of different examples. The first example is we're going to look at as the series that's constructed as follows. The second example, we're going to look at this one. And the third, we're going to look at, let's make it 2 plus 3 to the n over 5 to the n. And we're going to assume that each of these go from 1 to infinity. Okay, so we want to figure out, do these different series converge or diverge? And if they converge, we'd like to determine, can we say something specifically about what they converge to? All right, now each of these is going to require potentially a different technique. And again, I'll remind you, we have three things we've learned thus far: the nth term test. We've learned how to deal with telescoping series. And we've learned how to deal with geometric series. And as a general rule, I would start these problems by checking the nth term test. Then you're going to want to look to see if it's more likely to be telescoping or geometric. For geometric, it's pretty straightforward to recognize. If you see a bunch of things are all raised to the nth power, that's kind of a clue that might be appropriate. If not, then telescoping could be an option. Otherwise, we'll learn some more techniques later on. In this case, it turns out that the nth term test is going to be enough for the first problem. So let's look at the limit as n goes to infinity. So this is number 1 of an, or the limit as n goes to infinity of root n squared over n squared plus 2. And as it's written there, it's a little bit hard to see this, but you could multiply by 1 over n squared on the top and bottom inside the limit. So since we're multiplying by 1, that doesn't change anything. And this is going to be the limit as n goes to infinity now of root 1 over 1 plus 2 over n squared. And now we'll see that this term wants to approach 0 since the denominator is getting bigger but the numerator is staying the same size. And so this has got to approach 1. And so what that means is in the long run, this particular series behaves like we're adding 1 over and over and over and over again. Well, if you just keep adding 1 forever, you're definitely going to keep growing and growing and growing in terms of the sum. And so we'd say this diverges because an does not approach 0. And that's, again, the nth term test. All right, so we're done. It diverges. It doesn't approach any particular number. There's nothing else we can say. All right, the next one, we had root n plus 1 minus root n. And that one, the limit is going to be a little tricky. But the trick for this one is you can multiply what's called the conjugate on top and bottom. And this is a technique that basically is used to try to simplify expressions where you have a sum or a difference that's infinity minus infinity. In this case, notice the first term wants to go to infinity, the second one wants to go to infinity, so that's indeterminate. But if I multiply this out, I now have the limit as n goes to infinity of, well, square root times the square root, that's just going to be n plus 1. Then I'll have minus root n times root n plus 1, and plus root n times root n plus 1. So those terms are exactly the same, but with opposite signs. So they'll cancel. And then we'll have minus root n times root n, which is just n. And that's going to lead to some nice simplification here. We're just going to have the n minus n cancels, and we'll just have 1 over root n plus 1 plus root n. And so we'll see that the terms actually are approaching 0 because the denominator grows and goes off to infinity, and the numerator stays fixed at 1. Okay, so the nth term test is inconclusive. It only gives us an answer if we get something other than 0. If it gives us 0, then we can't say. And so it might converge, but it might not. It's not clear. All right, so that's out. We've ruled out the nth term test. Now, it does not look like a geometric series because we're not raising some constant to the nth power. So it seems like this has got to be telescoping. And so to solve this, we will start by writing out some terms. So A1, A2, and A3 look like, if I plug in 1 to this expression, I'll get root 2 minus root 1. If I plug in 2, I'll have root 3 minus root 2. And if I plug in 3, I'll have root 4 minus root 3. And so when we start looking at our partial sums, we're going to see a whole bunch of cancellation. S1 is root 2 minus root 1. S2 is root 2 minus root 1 plus the next term. And notice we have a plus root 2 and a minus root 2. So those cancel. So we'll get root 3 minus root 1. And then the next one will be root 2 minus root 1 plus root 3 minus root 2 plus root 4 minus root 3. And so even more cancellation happens. The root 2's and the root 3's will both cancel, and we'll be left with root 4 minus root 1. And notice I'm not trying to simplify these partial sums other than the simplification because I want to make sure it's really clear what the trend is. And sometimes when you simplify early on, it obscures what the pattern actually is. But now that we've left it this way, I think it's clear that the nth partial sum should be something like root, in this case, when we had S1, we had a root 2. When we had S2, we had a root 3. And S3, we had a root 4. So it looks like the thing under the first square root is always 1 higher than the subscript, minus root 1. And so our partial sums behave like a square root. And if we want the total sum then, all we need to do is take a limit as n goes to infinity of Sn and so we'll see that it looks like this one is going to be divergent because that square root term is growing, growing, growing. All right, last example, we had an equals 2 plus 3 to the n over 5 to the n from n equals 1 to infinity. And that looks, well, does not look so much like a telescoping series. Like we don't have any differences there. You can apply the nth term test here, but I'll just skip that part and for the sake of time. An does go to 0 here. So the nth term test is inconclusive. And so what we're left with is writing this as a geometric series. And so we want to compute the sum from n equals 1 to infinity of 2 plus 3 to the n over 5 to the n. And it doesn't look exactly like a geometric series right now, but if we do a little bit of algebra, I think we can actually show that it can be expressed in terms of 2 geometric series. So what we're going to do is we're going to first of all split this into 2 sums. The sum of 2 over 5 to the n plus the sum of 3n over 5 to the n. And that looks a little better. But remember, geometric series have to have some constant raised to the n power. And so this can be written as 2 times, well, we could write that as 1 to the n over 5 to the n, since 1 to the n is just 1, which means this can be written as just 1/5 to the n. And the second one, we could think of that as 3/5 to the n. We're just using some of our algebra rules to rewrite this. And now notice this first sum, it looks like the constant is 2. The ratio is 1/5. And in the second term, the constant is 1, and the ratio is 3/5. And so if both of these sums started with n equals 0, we could just plug into that formula that we had before. We said the sum from n equals 0 to infinity of c r to the n was c over 1 minus r if r is less than 1. And indeed, it is less than 1 for both of the two sums. So this is a convergent sum for each. But the problem is both of these start with n equals 1 instead of n equals 0. And so we're going to need to either subtract off the first term, minus, so we'll add the first term in, the n equals 0 term, and then we'll subtract it off. So that's the same as the first sum. And for the second one, we could write that as 1 times 3/5 to the n. We added the term with 0, and so we'll then subtract it off again. So that's one way. Alternatively, you can always just shift the index of your sum, write it so that n starts with 0, and that will basically adjust the value of the constant c. All right, so let's simplify this now. The first sum now looks like a geometric series with c is equal to 2 and r equals 1/5. And so this has just got to be 2 over 1 minus 1/5 minus, well, 2 1/5 to the 0 is just 2 times 1, plus the next one is 1 times 3/5 to the n, so the c is 1 and the ratio is 3/5. So we'll again use our geometric series formula, and then we'll subtract off 1. And so this has got to be 2 over 4/5 minus 2 plus 1 over 2/5 minus 1, which would be 10/4. If we flip that fraction, plus 5 seconds minus 3, which would be, well, that's just 5 halves again. So that's 10 halves when we add the two together. And so we'll have 10 halves, which is 5 minus 3, which is 2. Okay, so sometimes, although it may not be a geometric series right off the bat, if you split the sum up, if you apply some of your algebra rules and perhaps shift a limit or subtract off some missing terms, after adding them back in, of course, then you can sometimes use the geometric series formula to simplify a sum. I think you'll find that there are some questions like that on the web work, and so I wanted to give you at least one example to help you when you get to those. All right, good luck.